Okay, all right. So before I start with my talk, very cool to see that so many people are interested in CPU performance optimization. Very nice. My name is Leonhard. I'm working for Intel, and today I'm going to show you two easy ways to significantly increase the performance of Blender cycles running on CPUs. So with both approaches together, we reach a total speed up of around 23% for the Blender benchmark. So that's what you can see here. This is the total score we have here on the right. So this is measured on our current Arrow Lake S CPUs. So I mean, today most people want to render on GPUs because it's just faster. Yeah. But when you think about scenes in ArcViz or, for example, in movie production scenes, you very often run into a memory limit on your GPU because the VRAM is just too small. Yeah? And these scenes have to be rendered still on the CPU. Yeah? And I think this is also something that won't really change in the near future. And especially for these cases where we have, for example, a very large render farm that we have to render on, 20% better performance directly translates to 20% reduced costs, because we have to render 20% less time, we use the system, we use 20% less energy, and this directly translates to spendings. Good, so how do we achieve this performance gain? We have to go through two steps, and this will be the main agenda of my talk. On Windows running on x86, public Blender builds are currently built with MSVC. And this will be the first part of my talk. Switching to the Clang compiler gives us a significant speed up. So the first part of my talk will look into the differences between Clang and MSVC. And we will look at performance data to see where this performance gain is actually coming from. The second technique that we use to get the performance gain is adding hardware profile-guided optimization, or short HWPGO, to the compilation process. HWPGO is Intel's own flavor of profile-guided optimization, and it's designed specifically for a simple integration in build systems and very simple usage. And I mean, this will be the second part of my talk. I will introduce what HWPGO is. I will also briefly talk about profile-guided optimization in case you don't know it yet. And I will compare HWPGO to the established instrumented PGO. And finally, you will see how you can integrate HWPGO into your compilation process. So let's get started with switching from MSVC to Clang. And what I want to do on the first slide here is to give you a brief overview of what compilers we are looking at in this talk. So first we have MSVC, which is the standard Visual Studio C++ compiler. Then we have the Clang compiler, which is the C++ compiler of the LLVM project. And I also added Intel's ICX compiler to this comparison, which is our own LLVM-based compiler. And we add some custom optimizations to this. So MSVC, I think this is what most people use, is the de facto standard. It's the default compiler in Visual Studio. And with that, it also very heavily integrates with all the other APIs that Microsoft has to offer. So, for example, the Windows SDK, COM, .NET, DirectX, just to name a few here. Then in contrast, we have Clang, which is an open source compiler and maintained by the LLVM community. So this is something that the Blender developers should really like. It's a completely open source compiler. Clang comes with a MSVC-like command-line version, which is called Clang CL, and it has very mature compatibility with MSVC compiled binaries. So we can pretty much do a drop-in replacement. We take the MSVC build process and just put our Clang CL in, and we have compatibility with libraries, flags, and so on and so forth. Good. Because of its open source nature, Clang is also a very, very transparent compiler, and also very verbose. So Clang allows you to really trace down the whole process from source code to an intermediate representation. You can look at the optimization stages and how you get to the final binary. And I mean, this is very nice in a field like ray tracing or path tracing, where small differences in a result can already have a very, very big impact, can be very, very important. And Clang allows you, to just see why the compiler gave you a certain binary in the end. Good. Finally, we have our own ICX compiler, which is built on top of what Clang provides, plus optimizations that our compiler team implements just for the Intel architecture. And that's a reason why it's closed source, because it has some details on the architecture that we do not want to share. Most important is this thing is built on Clang, so we already use everything that's implemented in LLVM. And we also stream all optimizations that we do back up to the LLVM project. Of course, the community has to accept this, but so the work that our compiler folks do is also something that people in this open source project can benefit from. One example is the HWPGO method that I'm going to introduce in a few slides. This was something that was first developed in ICX and was then upstreamed to LLVM and is now open source. So when you want to port from MSVC to Clang, the main problem you will run into is that MSVC is used so heavily that it defines the behavior that people expect when implementing code that's undefined behavior. One example for this is aliasing. And this means that a ton of libraries that are commonly used were built to work with MSVC, and we often run into code that has errors or undefined behavior, but compiles with MSVC and fails with Clang once we try to switch to it. So porting to Clang always means cleaning up your code base. For Blender, this is actually super simple because Blender already has a very clean code base. There was not really much work required to get Clang CL here running. So what is not part of this talk, but what I still wanted to mention is the support for ISA of these compilers. So MSVC comes with our upcoming AVX 10.1 support for our upcoming AVX 10.1 vectorization. For Clang and ICX, we have support for AVX 10.2 and also APX, for which hardware will be available next year. Good. So let's compare the performance of Blender cycles built with these compilers. I already said we can use Clang CL just as drop-in replacement for MSVC. We can do the same thing for ICX, for our Intel compiler. What I use in this comparison are the standard compiler flags that are set for the Cycles project. So we have OB2, O2, OX. Cycles uses FastMath, so there will be a few differences in the output of in the result of the compilers, but that's the price you pay for FastMath. And we have vectorization with AVX2. And I didn't have to recompile any submodules with this. Good, so this is the performance that we get. Again, for an average of 6 runs. And here I'm looking at the Blender benchmark. Baseline is MSVC. And with Clang, we get a speed up of around 9.5% for Clang. And for ICX, it's 10.1%. And I also added this animal logic A-lab scene here as an example for a movie production scene. So for this scene, speed up is a bit less. It's around 6.5 for Clang and 6.7 for ICX. So you can see that just by switching the compiler without any further effort, Clang gives you a 6.5 better performance for a movie scene and 9.5 better performance for the benchmark, which is quite nice. Yeah, ICX doesn't add that much on top, so our custom optimizations give you around 0.5% for the benchmark and 0.2% for the movie scene. Good. So this brings us to the next kind of obvious question. Why is the performance of Clang better than for MSVC? And I mean, the truth is, this is a multitude of factors. We cannot analyze all of the reasons for it, but what I can try and what I will do in the next few slides is to look at an example analysis for the classroom scene. I chose the classroom scene because it's in the benchmark. It gives us a kind of nice. It shows us the most important points where the better performance is coming from, and for other scenes it will be relatively similar. So now there are two ways to look at performance. The first one is hardware counters, which pretty much every modern CPU has. So we have performance counters that tell us how often a certain instruction, for example, was executed. And from that we can conclude what changed with the compilers. And the second approach is to look at what actually changed in assembly. And it's not practical to do this for every function in Blender. Then we would have a day-long talk here. I will do this for a simple example. Good, let's start with the performance metrics. Here I have picked out a few selected ones that give us a very good picture of how the instructions change with the compiler. The two groups I present here are about vector register usage for floating point operations and integer operations. So here on top, these are events for scalar, 128-bit and 256-bit vector register usage. And we have the same thing for integers, 128-bit and 256-bit vector registers. Yeah, and I mean, what you can see is, so we get these vector registers give us a speed up because we can do the same thing we do with scalar instructions with multiple data, for multiple floats at once. Yeah? And what you can see is that Clang has a significantly higher usage of this 128-bit floating point vector registers. And because of that, on the other hand, the scalar instructions for floating points become less, yeah, by 10%. So this is one reason for the speed up. We see the same thing for integer vector registers. So better vectorization is one of the reasons why Clang gives you a better performance. The next groups look at conditional branch instructions. So this is what you would get, for example, an if-else statement. So these are the top two here. And a conditional branch can be taken, which means we jump in the code, or it can be not taken, which means we just execute the next instruction. Yeah? And because of that, non-taken branches, because we just go to the next instruction, are usually way easier to execute on a CPU. A taken branch, we have to find out what the target of the branch is. We have a lot of interaction with the branch prediction unit of the CPU. So a non-taken branch is, on average, cheaper to execute. And because of that, for an if-else statement, we want to have the more likely case to be the not taken case. Yeah? And this is also what we see here for Clang. The not taken case, we have 10.4% more often compared to MSVC. And because of that, the taken case is significantly reduced. Also something that Clang is doing better than MSVC. So then the last thing here, this is looking at stores and loads, so just store and load operations. For Clang, both are reduced, which is a hint for several things. This can be inlining. The assembly example that we will see on the next slide is about register usage, which is more efficient with Clang. Yeah, so you can see that we have less stores and less loads. Less instructions just mean better performance. It's as simple as that here. Good. So let's look at the register usage here. And I know this slide can be a bit overwhelming if you've never looked at assembly before. I will try to keep this as high level as possible. So this function here on the left, this is the triangle attribute float2 function, which you can find in the triangle header in the kernel geometry, in the cycles kernel geometry folder. And our performance analysis software VTune tells me that this function takes around 30% less time for the Clang build, which is quite significant. Yeah, on the left you have the code of this function, and I mean there's nothing really exciting happening here. We load two floating point values for it. We load two floating point values for the three vertices of a triangle. And then here in the arithmetics, we do triangular interpolation. Yeah, and the point we do this interpolation for is this u and v, which we load from this shader data struct. Yeah, so on the right, you have snippets of the assembly that were created by MSVC. Here we have the loads of the... Here we have the loads of the 6 floats to vector registers, so the 2 floats per vertex of the triangle. And in the part below, we load these 2 variables from shader data and the constant 1. Then we perform the calculation. These are all these arithmetic vector instructions that you see here. And now when you look very, very close to the assembly, you see that in between these arithmetics, we have these instructions here, which kind of do not seem to serve any particular purpose. It gets more clear when we look at the beginning of the assembly. So here in the beginning, we store the registers XMM8 and XMM9 to the stack. You can see that because the address here is relative to the stack pointer to RSP. And then after this register XMM8 is used in the arithmetics, we restore it from the stack. So this thing is called register spilling. What's happening is that what we're doing here requires a lot of registers. We have all these loads in the beginning to 10 of the vector registers. And because of that, the compiler thinks it must first free vector registers to store data temporarily, performs the calculation, and then recovers the whole thing from the stack. Yeah, and this storing data on the stack is what takes additional time. Yeah? So looking at Clang, I mean, you can see that this whole thing is way shorter. So here we have the arithmetic instructions, and the loads are for Clang directly put into these instructions because we can use them loading directly from memory. And that's how we get the 30% performance improvement. Okay, so all we did up to this point was switching the compiler, and this yielded better CPU performance. Yeah, just because Clang is doing a few things like vector register usage better than MSVC. So for the second part of this talk, I will go a step further and introduce a novel compiler technique which is called hardware profile guided optimization. Hardware profile-guided optimization is a technique based on feedback from the hardware. So all performance that we saw up until this point is based on classical compiler techniques. Yeah? So we have flags that we pass to the compiler. We have some hints in code that tell the compiler what to do. For example, the inline statement. And the compiler has some internal heuristic cost model to determine what to do. Examples for that are loop unrolling, inlining, auto-vectorization. So with profile-guided optimization, we upgrade these heuristics that are used in the compiler with an actual execution profile of how the application was executed on the hardware. PGO has been around for more than 20 years. The idea is to use this execution profile from hardware to create feedback for the compiler. And this enables additional and more precise optimizations. Because we now have the knowledge of how the application is actually executed on the CPU. Based on that, we can do more precise optimizations. So for inlining, for example, we can predict more accurately if it will give us a speedup or not. And we can also do new optimizations, as for example, conditional branch reordering, which is similar to what I've already shown for the Clang example, or basic block reordering or dead code separation. So I will have an example for this on a later slide. Additionally, I will use what is called link time optimization, which allows the classic optimizations as well as the profile-guided optimizations to be applied across translation units. So if you have multiple CPP files, you can now inline between those CPP files. Yeah? That's what LTO allows you to do. So this is the general compilation workflow for profile-guided optimization. We normally just build a binary specifically for profile generation. Then we create an execution profile by running this binary a few times for a set of representative workloads. And the workloads that we use to create this profile will be the ones the compiler optimizes for. And finally, we use this execution profile as feedback to the compiler and linker to get the optimized binary. So you see with PGO, you have to build your binary 2 times. Once with some sort of information with which we can create the profile, and then again, once we have the profile to get to the optimized build. So this is sort of the price for the better performance. The build process becomes longer, but when you think about it, it's not something you have to do for literally every build. When you develop, you can just stay with the unoptimized version, and then, for example, for a release or for a nightly build, it's enough to go to this process once. Yeah? So what has been out for a very, very long time is instrumented PGO. This is available in Clang, ICX, and MSVC. So here, for the first build, we add special instructions to the binary to instrument the application. Then we execute this instrumented build. The instructions we added write the profile. And we have to convert this raw data profile in a post-processing step into compiler input. And this profile already contains all information that we need for that. And then we feed this profile back to the compiler and get an optimized build. So instrumented PGO has one very big advantage. The profile is very, very accurate. So we just, the instrumentation just tracks every instruction that is significant for the profile, so you will get pretty much the best, the most exact result out of it. But instrumented PGO comes with several caveats. and this is the reason why many people do not use it in production today. So the instructions we add introduce a significant overhead. The binary becomes very, very large. And especially during execution, they have the effect that the execution becomes super slow because we have to go through all these instructions. So I had builds where minutes turned into hours because of this instrumentation. Then we have also changes in asynchronous execution. For Blender, this isn't really important because every thread is, for cycles, it's not really important because every thread is doing the same work in some way. But think of a game where threads have completely different tasks. This can be a huge problem because the execution completely changes. And finally, the profiles are very hard to reuse because we store everything in the profile. When we change the code, we can't easily reuse it. Yeah? So the solution for that Intel developed is called hardware profile guided optimization. And this approach tries to work around all these issues that I just presented. So for HWPGO, for the profile generation, we can use a release build and just require debug symbols with it. And instead of instrumentation, we just use performance counters that we sample. So Intel CPUs have special performance counters called last branch records that give us the same information the instrumentation of PGO gave us. And then we post-process these performance events, and using the debug symbols from the first step, we can map the counters back to source. And turn them into a profile that we can feed back to the compiler. So this approach works around several of the problems we had with instrumented PGO. We profile a release build. So collecting information for the profile has pretty much no execution overhead. Also, for threading, the whole thing doesn't have any influence. On threading, it doesn't have any influence. And finally, when we do the mapping back to source, we can also reuse these profiles. There's one disadvantage of this approach. The accuracy of our sampling has an influence on how good the outcome is. But this is essentially a convergence problem. Yeah? The longer we sample, the finer our sampling is, the more we actually converge to the performance that we need. For the experiments that I did for cycles, I had to sample for 30 seconds, and this already gave me the best performance, the same performance that we had for instrumented PGO. Good. I want to do a brief look into what is profiled and what information we get out of this. So LLVM has this inherent model of the program structure, which is called the control flow graph. So take this code snippet here in the middle, this code snippet here. Every execution, every function, every instruction here is executed linearly from top to bottom. Only when we run into branches like functions or this if-else statement here, for example, this is when the path of the execution changes in the program. Yeah, and this kind of allows us to model the program as a control flow graph. We have nodes which are continuously executed instructions. So, for example, the body of a function where we have no if or else statements. And every branch, like this call to a function here, is the edge of this graph. Yeah, and LLVM already has this graph as inherent model, and all the optimizations that we just saw use information of this graph to do optimizations. Yeah? And program execution through this program execution is just modeled as a traversal through this graph. Yeah. So we can go through the whole thing and know how which instructions are executed. Good. So when we compile with Clang without PGO, optimizations already use heuristics of weights of this graph. This is what we saw in the performance data in the beginning for the taken, non-taken example. But with PGO, we can be more accurate. Yeah? And we can fill this with actual values. So Intel CPUs, I already said that. So Intel CPUs have what is called last branch records. This is a very large set of registers that we have on our CPUs, which just track the last 32 taken branches with their target. And if we sample that, we just sample traversals through this control flow graph. And if we do this often enough, we get an idea of which blocks are executed very often, which branches are executed very often. We know what hot blocks are, we know what cold blocks are. So one optimization that only works based on this data, I wanted to also give you an example for this, is called basic block reordering and dead code separation. So from the profile, we know which blocks in our control flow graph are hot and cold. And what we can do with this is that we just cluster all hot blocks together and separate the cold blocks from the rest of the code. And the effect of this is pretty much the same you want to do with your data. Yeah? You want to have hot data close to each other and cold data away from the rest. So here we're just doing the same thing, just for instructions. Yeah, and this improves two components on a CPU. The instruction cache, which works very much like a data cache, becomes better, and the instruction translation look aside buffer, which is a unit to translate addresses, becomes also the accesses to this also becomes better because we have more accesses to the same pages, to the same instruction pages here. Good. So when we implement HWPGO for Blender cycles, this is the speed up that we get in total. So and in this plot I have the ICX numbers in gray, and then on top the total numbers for ICX and HWPGO. And here I show the data for here I show the data for ICX and not for Clang. The method that we pushed to the Clang repository is exactly the same, so you will see the same delta here. So as profile, I use the 3 scenes from the Blender benchmark to create the profile. And you can see that these 3 scenes have the highest gains, which makes sense because we profiled them. Yeah? So especially for the monster scene, it's a 26.6% speed up. But you can also see that we have a good speed up for other scenes. So take this barbershop interior scene here, which wasn't considered in the profile, still a 22.0% speed up and 8% coming from HWPGO. So I have the average of all scenes here, 6% of all scenes that we tested here, 6% for ICX, and HWPGO adds around 7% on top of it. So one thing I also wanted to show is this cloud scene here. So here for ICX we had a speed up of 8%, and HWPGO actually degraded the performance here. So this kind of shows us the profile has what we profile has a very high influence on the performance. And if we do not pick the profile the right way, well, we can even get a performance degradation. Yeah. Yeah. So I mean, for these results, I profiled the 3 scenes down here for 30 seconds. And the goal was to create a general speed up, for all of cycles. What you can also do with HWPGO is to optimize just for a dedicated scene. So the idea here is that you have a scene that you render 100 times for multiple hours because of a very long animation, for example, or because you edit it very often and then want to look at the final result again. What we can do with HWPGO is we profile this single scene once and then reuse the profile, use the profile to build it, and then reuse this optimized build just for the single scene. Yeah. This is what you get for the ALAP scene. So for MSVC, that's the baseline. Then ICX adds 6.6% performance, and with this, with the general profile, which I showed on the last slide, we get a 16% speed up. And if we do it with a special profile just to the single scene, we even get 3% better performance out of the whole thing. So I mean, these are the two ways you can use HWPGO. So quickly, what happens with the instructions when we optimize with HWPGO? So this is again for the classroom scene. We have, this direction. We have 30% less calls, which means that 30% of function calls are now inlined. This is one result of HWPGO. The conditional reordering works better. So we have 24% more non-taken branches, 34% less taken branches. So same effect that we saw for Clang before. And finally, the two metrics I talked about for basic block reordering, stalls of the CPU because instructions weren't found in the instruction cache are now 27% less, and ITLB misses, so that's this address resolving unit, are 50% less. Good. So to come to a conclusion, you get a lot of performance out of Blender cycles when you switch from MSVC to Clang. 9.5% better performance for the benchmark because of better usage of SIMD registers, more efficient execution of branches, and less loads and stores based on better register usage. And with HWPGO, you get better performance through hardware feedback. This adds around 12% performance for the Blender benchmark. And we get the speed up through better inlining, basic block reordering, and if-else reordering. Good. We are not the first ones to work on these approaches. So everything, all this HWPGO stuff has been done before. The first ones to use last branch records were the AutoFDO team at Google. And there are also these two approaches which do something very similar. First is called Bolt, which does binary editing based on a profile. And the second one is Propeller, which does post-link optimization. So if you're interested in that stuff, check out those papers. Yeah, and this is my last slide. So for HWPGO, we have a tutorial online. There you can see the flags you have to use, how you sample the last branch records and everything. And we have an article where we already integrated this successfully into a well-known path tracer, that you also saw at this conference. Yeah, thanks for your attention. Do you have questions? Yes?
Yeah. I didn't quite get whether for the HWPGO you also enabled link time optimization?
Yes. Yeah.
Do you have numbers with HWPGO but with link time optimization?
So link time, I don't have them here. Link time optimization usually gives you 2 to 3% for cycles. That's what I saw. The important part is, let me just jump to that slide. So we use, so that's HWPGO. We do not use LTO for the profile generation because then these debug symbols here, when you do inlining over object files, it becomes a bit obfuscated. And here in the optimization, I use LTO then in the results. Yeah. Yes?
Sorry, I kind of missed the very beginning of the talk, but is this available on platforms other than Windows? Like, do you support this at least on Linux?
Yes. So you have HWPGO as well in Clang, and also in ICX for Linux.
Is it upstream Clang as well, or is it a special form?
No. It's in the upstream Clang. Yeah. I don't have the link here, but you can easily find it in the Clang documentation. Yeah. It's called I think it's called sampled profile guided optimization. Yeah. Yeah.
Does it interact with VTune at all as well?
So you need some way to sample these performance counters. You can use Linux Perf if you're on Linux for that. VTune is one of the options. Yeah. Yes.
Does the basic block reordering try to cluster things according to what phase of the program is running?
So you have, that's a good question. I do not think it's considering any temporal dependencies. So this is really just spatial, spatial considerations. Yeah.
You mentioned the sampling phase to get performance counters.
Mm-hmm.
This would be a manual step in the build process.
You can automate it. Yeah. In the end, so what we did in this production ray tracer is you can run everything from CMD, and we automated it with a long Python script. Yeah.
Do you have any experience or insight how well this generalizes to other like microarchitectures or even ISAs? Because I would imagine that the control flow optimization is fairly universal, probably.
Yes. Yeah. So when you talk about other ISAs, so ARM, for example, I haven't looked into this, to be honest, but I mean, that's one of the ideas behind Clang, right? That you can change the backend and do similar optimizations. So just try it out. And you get these results. So if you look at other x86 CPUs, you also get the same performance gains there. It's very similar. Yeah.
One follow-up on that: when you mentioned you tested this in Arrow Lake S, did you do the MRH native to optimize for that in the compiler, or is it just the generic x86?
So I just used what public cycles uses. So these are the flags here. So we have just Arch AVX2 that I use here. Yeah. I think Arch native would give you. No, it should be still AVX2, huh? Should be very similar at least. Yeah. Yep, you had a question.
This presentation is great. It's focused to cycles, but Blender is really huge. It's a lot of different use cases and sample points. Are there ways how to merge profiles together, or to sample specific for a specific feature, like something?
Yeah. So that's part of the idea here. You need a representative workload, whatever that is. You can also click through a GUI if you want, and in parallel you sample the performance counters, and that's what you feed to the compiler, and for that you get an optimization. But you get the optimization. So this makes sense if you have a high workload on the CPU, and that's why I took cycles as an example here. Yeah.
So because your only result then is a profile, I guess what you're just trying to say is like, because they're working on Blender, the cycles guys want to improve their bit, but so do the animation guys, and so do the other people.
Yeah.
You can't have one person load up the profile and then run a cycles window, do an animation, and then extra thing to get one profile.
Okay. My bad. You can merge profiles. It's as simple as that.
Awesome.
You can do single steps and then merge everything in one profile. Yeah. And the thing you have to consider is that you might get, depending on what you profile, you get different performance results out. Yeah. So, I mean, this is all cycles now, but say there is some concurrent thing happening between animations and cycles, you would have to figure. Yeah.
So that's kind of the primary reason why you use cycles is, I guess, because cycles conveniently has good benchmark scenes that are I mean, you could do the same for like geometry nodes or animation, whatever. It's just
Guess there's nothing yet available on that side. But we just talked about it. And I mean, cycles is one of the applications you would run on a very large system. Yeah, that's also part of the reason. Yeah.
If I were to try this elsewhere, I would be a little concerned about overfitting to the specific workload I tested.
Yep.
Is there like a confidence metric that it takes into account? Like, I know that inlining this certain function will make this workload much faster, but it may make something else slower.
So
how do you think about that?
So that's something we're working on, but it's very hard to predict what performance outcome you have from the profile. It's so for this production ray tracer, it was mostly trying out. Yeah. And,
I guess my takeaway would be that the safe part of this talk is the first one. We should just switch to Clang.
Yes, of course. That's the easy one, yeah. So this thing, it's a bit more tricky, but yeah.
Can I ask as well? Like,
yes.
The profiles seem like they end up as a little bit of a black box that you then chuck into the compiler later. Is there any way to get insights that can be directly translated into code changes rather than the black box being passed to the compiler?
So what you see in the profile is a mapping. So the profile can be transformed to a text format, and in this text format you can see the branches and basic blocks traced back to symbols of your source. So you have function.
Put a notice guide here, or put a not taken here, or something like that.
Yeah. So you the profile just contains counts. You do not know what the compiler will do with it in the end. That part is a bit black box.
Yeah, that's what I'm asking about. It's a nice mapping back to an equivalent source code change that would get you the same result as the profile.
Yeah, more or less you can derive that from there. Yeah. Yes?
I know this isn't really what your talk was about, but I'm interested in data layout optimizations. Is this something that you're also looking at?
So I mean, this is obviously something you could implement in this. So yeah, we're looking into it. Yeah. The main problem here is that you do not have the right performance metrics yet available. Yeah, that part is missing. But what you can, for example, do, which has already been done for a few years, is optimizing the data layout of the global static data section. So that works because your linker gives you a mapping from virtual address space to the symbols that you have in there. I think the MSVC linker already provides some flag. So this goes in the same direction.
There's very little global data these days.
Yeah.
The method of compiling this and getting those like branch counters, is that specific part Intel specific if you're compiling through Clang, or is it genericized across x86 at least?
Sorry,
So the feature that you're utilizing by calling into Clang to enable the counting of the branches, is that Intel specific then?
So the Intel specific part is this last branch record.
Yes. So there's not an equivalent for other architectures?
Yes. Yeah.
There's a C++ feature, I work in C++ programming, where you can annotate an if statement with likely or unlikely.
Yeah.
I guess that's just like a very low-tech version of this.
Exactly. Yeah.
Yes. Is there significant gains to annotating code, or is it just a better idea to go directly to this?
So see it from this side. You have so many branches in your code. It's very, very hard to really figure out for each where you should place this likely or unlikely statement. This thing does the job for you in the end. Yeah.
I guess your manual annotations might no longer reflect reality after a while.
They're overwritten in that case.
That's kind of like what I was trying to do before, but because it's generic, then you don't need the profile later to get the same result. Very cool.
Yeah.
Thank you.
Good. Yeah.
When the code changes, do you have to rerun the profiling again and again?
So this is kind of one of the advantages here. You can reuse the HWPGO profiles because you have this mapping mechanism with debug symbols. The more your code changes, the worse your performance gets. Yeah. So if you have major rewrites of functions, it's better to redo the profile. Yeah.
So it could be that if you have the same symbol name and you make it really different and you apply the profile, it will do the wrong branch.
So I don't think, so the profile contains information about the branches in your function, and it can detect if that part changed very significantly, and then you won't have any optimization at all. Yeah. So you won't run into a bad optimization because you can probably enforce a case where you do, but yeah. Yes?
Is there a good way in Clang to get information about what decision changed based on the profile compared to what the compiler would do by default?
So Clang allows you, depends on what you define as good. Clang allows you to dump intermediate representation between optimizations, and that's the part you need to be able to interpret. But then you can see what HWPGO actually does.
I guess I was mostly interested in, like, at some points in an optimization pass, like this has to make a decision, I inline or I don't inline, or I change the order. And at that point it would just log out, okay, by default I would do this optimization, but because I have this profile, I do another, and I do it differently.
Yeah, so you can, so Clang allows you to directly look at the optimization passes that you have, and you will see the actual score of HWPGO that HWPGO passes, and then why it made the decision. So what's very cool, if you want to look at this, the Compiler Explorer has a feature that allows you to parse through optimization passes, through IR and optimization passes of a code snippet. Yeah. Good, okay. There are no more questions. Yeah, thanks for coming.